In this session of the chemistry of alkynes, we will learn about another type of their reactions, and this type is hydration. And hydration of alkynes can be of two types in general: mercury-catalyzed hydration and also hydroboration oxidation, as we saw when we talked about the reactions of alkenes. Hydration reactions of alkenes are of two types: oxymercurations, if you recall, and also hydroboration oxidation. Okay, the reactions here are not very different actually. So alkynes undergo hydration reactions that can be catalyzed by mercury, or that can be done in the or via the process of hydroboration oxidation. Remember, hydration is basically, in effect, reaction with water or addition of water to an alkyne. But as we learned before, alkynes can be of two general types, okay, structurally, depending on where the position of the carbon-carbon triple bond. Alkynes can be terminal or internal. So this is the general structure of terminal alkynes. Remember, terminal alkynes have the carbon-carbon triple bond at the terminus or at the beginning. Now, the mercury-catalyzed hydration reaction in this case is not termed oxymercuration. The conditions are slightly, although not very differently, very significantly different from that of the oxymercuration reaction of alkenes. Okay, the reaction is similar, the conditions are slightly different. Okay, so these are the conditions: mercury 2 sulfate, mercury 2 sulfate. So this can be also specifically labeled as mercury 2 catalyzed hydration. That would be accurate. Mercury 2 sulfate in the presence of sulfuric acid, and it's aqueous, so in water, obviously, yeah, aqueous solution of sulfuric acid. These are the conditions of the mercury 2 catalyzed hydration reactions of alkynes. This is basically an indirect addition of water. So addition of H and OH, if you remember. Yeah? Addition of AB in general, AB, yeah, so H and OH. So H will bond to one carbon of the carbon-carbon triple bond, and OH will bond to the other carbon. So if you look at these two carbons of the terminal alkyne, you will see that carbon 1 has one hydrogen, and carbon 2 has none, which means H of H2O in this hydration reaction will bond to carbon 1 following Markovnikov's rule, which means Markovnikov's rule applies here. Hydrogen from water will bond to carbon 1, and OH from water will bond to carbon 2. This is addition reaction of water, by the way. Remember, yeah? So hydration is addition. It's actually indirect addition of H2O. You can view H2O as HOH if you take, or if you want to relate this with the general representation of the AB molecule. Yeah? So H will bond to carbon 1 following Markovnikov's rule, and OH will bond to carbon 2. So this is the intermediate that is obtained. Carbon 1 now has two hydrogens, and carbon 2 has OH. Yeah. So this is carbon 1, and this is carbon 2. Carbon 1 now bonds to two hydrogens as a result of this addition reaction of water or hydration reaction that is catalyzed by mercury 2 under these conditions. This is the intermediate product that's initially formed. And we say initially formed because it's not the final product. This will undergo a special type of rearrangement. Yeah? But before we talk about that special type of rearrangement, let's look at the functional groups that are present in this molecule. This molecule has here a carbon-carbon double bond. So it is an alkene. It is an alkene. But also, if you look here also, it has an OH, which means also it is an alcohol. So it's an alkene and alcohol. Alkene can be denoted by ene, and alcohol can be denoted by ol, like methanol, ethanol. Yeah? And that's why the general name for this type of compound, which has a carbon-carbon double bond between two carbons, and there's OH on one of these two carbons that are doubly bonded, this is described or termed or named as enol. Enol. En means the compound contains a carbon-carbon double bond. Ol means the compound contains a hydroxyl group, or it is an alcohol. So this is an enol. Enol. So ol to indicate an alcohol, and ene to indicate an alkene. An alkene. Enol, like E9 before, compound with a double bond and a triple bond. Diene, a compound with two carbon-carbon triple bonds. Diene, a compound with two double bonds. This is enol, a compound with a carbon-carbon double bond and a hydroxyl group. Now, enols are not stable. They will undergo a rearrangement reaction that will result in a more stable molecule, or product that is more stable than the enol itself. So this will undergo a special type of rearrangement that is actually called tautomerism. Tautomerism. So this is tautomerism. That will convert the enol into a methyl ketone. This is a methyl ketone. Carbon 1 had two hydrogens. Carbon 1 now has 3 hydrogens. Carbon 1 had 2, carbon 1 now has 3. Carbon 2 had oxygen and hydrogen. Carbon 2 has oxygen only. So that hydrogen from the OH group has now gone to carbon 1. It is a rearrangement reaction. Overall, specifically, it's called tautomerism. This is a methyl. This is a methyl ketone. So it's a tautomerism between the enol and the ketone. That's why this tautomerism reaction is called keto-enol tautomerism. Keto-enol tautomerism. Yeah? Because this is the ketone form, if you like. This is the keto form, or keto tautomer actually. You can label it like this. This is the keto tautomer. This is the enol tautomer. And this tautomerism, which leads to the formation of the ketone from the enol, is keto-enol tautomerism. Keto-enol tautomerism, and the reason why this takes place is thermodynamics. The keto tautomerism is more stable. This is more stable, and that's exactly why this rearrangement or tautomerism reaction takes place, because the product is more stable, its nature, its thermodynamics. So therefore, a terminal alkyne can lead to eventually a methyl ketone in mercury-catalyzed hydration reaction using the conditions specified. What if we take an internal alkyne? What if we take an internal alkyne? Again, as we said before, for simplicity purposes, again, we take a symmetrical internal alkyne, and we write the same conditions, mercury to catalyzed hydration conditions. So at mercury 2 sulfate in the presence of sulfuric acid in water, aqueous sulfuric acid. The result will be similar, by the way, but again here, if you, as we learned before, when we added HX to internal alkynes, the two carbon atoms of the internal carbon-carbon triple bond do not have hydrogen. So therefore, Markovnikov's rule does not apply in this initial hydration step, in this mercury-catalyzed hydration. Yeah? Okay. So this is the product that's obtained. One H will bond to one carbon, so you can name them again AB. One H will bond to one carbon. If R and R are the same, by the way, there's no difference between these two carbons. So it doesn't really matter where H bonds to, which carbon, A or B. If the hydrogen from water, remember addition of H and OH, this reaction, yeah? It's hydration, yeah? Okay, so H will bond to carbon B, for example, and OH will bond to carbon A, like this, yeah? So H will bond to carbon B, and OH bonds to carbon A. Okay, if you look at this structure, you will also notice that it is an enol. So the structures here are actually not very different at all from each other. This has only an additional R, but still, it's a compound with a carbon-carbon double bond, and also it has an alcohol. So this is an enol. This is an enol intermediate. But enols, as we saw before, they will undergo tautomerism to the corresponding ketone. That's because the ketone is more stable than the enol. Yeah? So this will lead eventually to this ketone, where carbon A now will have the carbon oxygen double bond, and carbon B will become a methylene. So this is carbon A, and this is carbon B. This is a ketone, okay, and this step is also keto-enol tautomerism. This is also keto-enol tautomerism. So this is the final product. It's an internal ketone, by the way. It's not methyl. This is also an internal ketone, obviously. Yeah? Okay. This is a methyl ketone specifically, where the ketone or the carbonyl group of the ketone is at carbon number 2. But here it's further in, if you like, in the chain. Yeah. Okay. This ketone is produced. One asymmetrical internal alkyne is hydrated using mercury to catalyze hydration reaction. If the alkyne or if the internal alkyne is not symmetrical, there could be two ketones produced. If R and R are not the same, there could be two ketones produced. But this is something that we said also before, that if the internal alkyne is not symmetrical, then the number of products will be different. The other type of hydration reactions that alkynes can undergo is hydroboration oxidation. We learned before about mercury-catalyzed hydration reactions of alkynes, which result in formation of ketones. Now we learn about the hydroboration oxidation reactions of alkyne. This is also hydration reaction, by the way. So effectively, it's addition of water. Remember, it's addition of H, if you like, and OH to a carbon-carbon multiple bond. So hydroboration oxidation. This is hydration. Hydration reaction. It's addition of water. So addition of H and OH to a carbon-carbon multiple bond. We begin with terminal alkynes as usual. So this is the general structure of a terminal alkyne. Terminal alkynes have carbon-carbon triple bond at the terminus or at the beginning. The hydroboration oxidation reaction conditions here are not different at all from those of alkenes, which means they involve two steps. The first step is addition of borane BH3. Addition of borane BH3 which is the hydroboration step. The first step is hydroboration. The second step is oxidation, which employs hydrogen peroxide and sodium hydroxide. Hydrogen peroxide and sodium hydroxide. So hydroboration is the first step, oxidation is the second step, and that's the origin of this of the reaction name. Now, we learned before that the hydroboration reaction of alkenes is controlled by sterics. The addition of borane can be viewed as addition of BH2 unit and H. Remember, AB, BH2 and H to a carbon-carbon multiple bond. Now, the BH2 is bigger in size. So that BH2 unit, or a group of BH3 of borane, will bond to the more accessible carbon of the carbon-carbon multiple bond. This carbon, or carbon 1 of this terminal alkyne, is more accessible. This carbon 1, is more accessible. More accessible means it has less steric hindrance. More accessible or less hindrance, or less steric hindrance, or less bulky. Yeah, all of these terms are correct. Carbon 2, on the other hand, is less accessible, or more sterically hindered. So this is more hindered or less accessible. And therefore BH2 from borane will bond to carbon 1, and H from borane will bond to carbon 2. Again, what controls the reaction is sterics. BH2, the bigger unit, or BH3, will bond to the more accessible carbon, which is carbon 1. H, the smaller unit of BH3, will bond to the less accessible carbon of this terminal carbon-carbon triple bond. So the product will be this. So an intermediate product where there is BH2 that is bonded to carbon 1 and H that's bonded to carbon 2. So this is an intermediate that's possible to be obtained. In the second step, the oxidation step, the BH2 will be converted into OH. So this is H2O2, hydrogen peroxide and sodium hydroxide. So this is the product of this step. And again, if you pay attention, you will notice that this is an enol as well, because it contains a carbon-carbon double bond and also a hydroxyl group or an alcohol. But enols undergo tautomerism to the more stable ketone. So this will undergo tautomerism to the more stable carbon alkene bond. It's not going to be a ketone, of course, here, because the OH is on carbon 1. So this is going to be to undergo this type of tautomerism. Carbon 1 will now be doubly bonded to oxygen. Carbon 2 will take that H from the hydroxyl group. Okay, this is the carbon bond that's obtained. But if you pay attention, the carbonyl group, or the carbonyl unit, is actually on carbon 1. Carbon 1 has a hydrogen. Carbon 1 has a hydrogen. So this is now an aldehyde specifically. This is, of course, not a ketone. This is an aldehyde, which means terminal alkynes lead to aldehydes eventually in hydroboration oxidation reactions. Yeah, an aldehyde is obtained in this case. So this is the product that is obtained when a terminal alkyne is treated with the hydroboration oxidation conditions. If we take an internal alkyne, that's also symmetrical for simplicity reasons. Yeah, so this is a symmetrical internal alkyne. If we take a symmetrical internal alkyne and then also we treat it with the same conditions. So borane as the first step in the hydroboration step, and in the second step, the oxidation, which employs hydrogen peroxide, sodium hydroxide. Here, by the way, these two carbons are the same from a sterical point of view, from hindrance point of view, if you like. Yeah. Okay, BH2 from borane, okay, can bond to any of these two carbons, or H from borane can bond to any of these two carbons, and therefore this type of intermediate could be obtained. So H here, BH2 here, and we could also, as we did before, we could label these carbon atoms with AB, these general symbols AB, and during the oxidation reaction, that BH2 will be converted into a hydroxyl group. So this is the kind of intermediate that is obtained. And again, this is an enol. Okay, so the enol is obtained during this oxidation step involving hydrogen peroxide and sodium hydroxide. The enol is not stable. It will tautomerize to a more stable carbonyl compound. The carbonyl compound here will have then a double bond, a carbon oxygen double bond on this position. And of course, since this is already inside, yeah, it's going to be a ketone. Yeah. So this enol will then tautomerize to the corresponding ketone. So this is the ketone that is obtained, and all of these steps are T2 enol tautomerism. T2 enol tautomerism will lead to the ketone from the enol. So therefore, a ketone is obtained if an internal alkyne is treated with the hydroboration oxidation reaction conditions. If the internal alkyne is not symmetrical, a mixture of ketones is obtained. So not only one, actually two, if R and R are different from each other. If R and R are the same or identical, which means the alkyne is symmetrical, then one ketone is obtained. So to summarize this, terminal alkynes lead to aldehydes in the hydroboration oxidation reaction, whereas internal alkynes lead to ketones.